Welcome everybody once more to the official IAU G2 online conference series. As usual, this is about massive stars. And today is my real pleasure to introduce our next speaker, Elizabeth Stanway. She's presently a professor in the Astronomy and Astrophysics group at the University of Warwick in the UK, a position that she has been holding since last year. She presented her PhD thesis in September 2004 at the University of Cambridge, which had a very intriguing title, Probing the End of the Dark Ages. I'm curious to see what was it about. After that, she moved to the US as postdoctoral research associate at the University of Wisconsin-Madison, and a couple of years later, she came back to UK to hold a similar position at the University of Bristol. In 2010, she was awarded the Royal Astronomical Society Winston Capital Prize. Just at the time, she was moving back from Bristol to Warwick to stay there until now. Beyond many interesting research activities, which can be found in her CV, I can also mention that she's actively involved in undergraduate and postgraduate teaching in physics and astrophysics, and she's very experienced at presenting astronomy to general audience and public talk. Scientifically speaking, her main research interest is in the study of distant galaxies, taking a multi-wavelength approach to explore different components of the galaxies and the nature, lifetime, and behavior of star formation and early times of the universe. And more specifically, she works in projects covering a variety of topics such as spectral synthesis, including massive binaries, Lyman break galaxies at high redshifts, also including the study of local analogs, GRBs and GRB host galaxies, and molecular gas and dust at high redshifts. Last but not least, she also has sign interest in the role of science fiction in popular understanding of science and also the story of astronomy. So definitely quite an interesting person to enjoy a nice conversation with a coffee or a beer. So once more, thank you very much, Elizabeth, for accepting the invitation of the IAU G2 Commission. We are really glad to have you here. Whenever you want, the floor is yours.
Thank you very much. It's an honour to be asked to speak to you all, and I hope I will live up to that very nice introduction. I am indeed Elizabeth Stanway. I'm at the University of Warwick. We're a quite varied group here with an emphasis on time domain astrophysics, so things that change over time. I will admit I kind of sneaked in on that with an interest in gamma ray bursts and supernovae, but my primary interest from the beginning of my PhD was in the distant universe. And when we say probing the end of the Dark Ages, we mean the cosmic Dark Ages. So the epoch of reionization and the way that the universe evolved in its first billion years. And I was fascinated in galaxies. I had colleagues who were fascinated with stars. In particular, I have to mention Jan Eldridge, who I have been working with since we were first year physics undergraduates, we were lab partners in our undergraduate physics labs. Jan's PhD thesis was on stellar evolution and supernova progenitors. But the more that Jan and I ended up speaking to one another, the more we realised that when it comes to understanding, galaxies are made of stars. Now, this comes as a surprise to a remarkable number of people. Often when I'm speaking to extragalactic galaxy people, audiences, I tend to put my massive stars hat on, and I really emphasise the importance of stellar evolution. When I'm talking to massive stars audiences, I tend to do the reverse and point out that we do need to understand stars before we understand galaxies. But the galaxies which we observe are fascinating laboratories in which we can interpret, understand, and explore the properties of stars. This is particularly true of massive stars, since in distant galaxies, we find environments, compositions, and stellar population ages which are typically rare in the local universe. So the fundamentals of what I do, and what Jan and I have now been doing for an embarrassingly long time, I was going to put a date on it there and changed my mind, is stellar population and spectral synthesis. And this isn't a new idea. This concept of SPS codes can be traced back to New Zealand astrophysicist who moved to America called Beatrice Tinsley. And back in the 1960s, the late 1960s, she calculated 13 stellar evolution models at 1 gig a year intervals. And she said, what happens if I add together stars of different ages? Does it look anything like a galaxy? And she concluded that it did. And this fundamental work really laid the foundations for the idea that when we look at the integrated light from stellar populations, be it the light from galaxies, distant galaxies, from stellar clusters, or even resolved stellar populations nearby, we need to consider the distribution in age and other parameters of the stars which are contributing to that population. So the overall picture of population and spectral synthesis is relatively straightforward. It starts from the assumption that we understand stellar evolution. Now, I will come back to question that assumption later, but let's say that if we have a sun-like star, we can calculate its evolution with time. We can do the same for massive stars, we can look at post-main sequence evolution, and we can calculate how stellar remnants cool or interact with other stars over time. If we then take a stellar initial mass function that tells us how many massive stars we have compared to low mass stars, then we can undertake what's known as population synthesis. This gives you a composite stellar population at a given age, so it's very useful for calculating things like Wolf-Rayet to O-star ratios or red supergiant to O-star ratios or similar. Since you're working with stellar population models, you're working in the theorist's parameter space, so you can calculate luminosity temperature HR diagrams. And you can also calculate things like supernova rates and the remaining stellar mass in a population as the more massive stars die off over time. Now, for many applications, particularly in stellar astrophysics and with unresolved stellar population, and with fully resolved stellar populations, that is sufficient and it gives a lot of important information. But if you wish to compare against observations, and in particular observations of unresolved stellar populations, you need to undertake an additional step. This is stellar spectral synthesis, and it assigns a spectrum of appropriate temperature, gravity, surface composition, and potentially other properties to each model at each time step. So the output of a population and spectral synthesis code comprises the composite spectrum of an unresolved stellar population, the photometric colours of that population, or indeed of the individual stars in that population at a given age, colour magnitude diagrams, this time in observer space, and properties such as absorption and emission lines. This again is a well-established technique since Beatrice Tinsley's early work. A lot has been done. Her initial 13 stellar evolution models has been superseded, and people since the 1990s have been running very large, computationally demanding population and spectral synthesis models. But until the last couple of decades, there was a major omission, and that omission was to completely ignore one of the most interesting aspects of stellar populations, which is the fact, and the very obvious fact to this audience, that the majority of massive stars reside in binaries. So this is some recent work. Well, I say recent, it's a decade old now. That just shows how I'm getting older. This is some work by Mo and Di Stefano, who did a meta-analysis combining information from many techniques and many surveys in the local universe to determine that the average number of companions for massive stars is actually typically greater than 1. These stars are far more likely to be in binaries than they are to be single. For those interested in older stellar populations, it's tempting to say binaries aren't important because only 15% of stars like the Sun are in binaries. But as you move towards lower metallicities, it's now very clear that that binary fraction also goes up. So at low metallicities, even the low mass stars are also in binaries. Now, as I say, that's probably obvious to this audience, but I've spent a substantial fraction of my career persuading those who work purely on observations of distant galaxies that binary models are important, because the spectra of young stellar populations are dominated by the most massive stars, and we know that 70% or so of those massive stars interact with a binary partner in their evolutionary lifetime. The next point is debatable and needs more work, but it's fairly clear that these interactions are strongest at low metallicities. And that means that for anyone who is looking to study how the chemical composition of the universe evolved, how the galaxies in the universe merged, the impact that had on the history of star formation, and all who wish to test the physics of low metallicity massive star formation, it means we can't ignore the binaries in emission line galaxies, because they are providing a substantial fraction of the flux, and interpreting that flux can provide constraints on the stellar evolution as well as on the galaxy evolution. So I'm going to whiz through this because this is a seminar rather than a lecture, but we need to take our population and spectral synthesis framework, and now we need to add to it, because we need binary stellar evolution tracks. And these are going to be a function of mass, as the single star tracks were, and of course metallicity, but they're now additionally going to be a function of the initial period of the binary, whether they're born close or far apart, and the mass ratio of the binary. Are we looking at a twin system or a system with a high mass ratio? We have to do an awful lot of additional physics for binary stellar evolution tracks. We have to consider mass transfer between the systems, the impact this has on stripping, potentially even common envelope evolution, the impact of material that's accreted through rejuvenation and mixing, and potentially rotational spin-up from the angular momentum carried by that material. This is all going to impact the evolution of the binary parameters, this separation and mass ratio. And we're going to have to look at what happens when the most massive star, or the first star, let's say, reaches the end of its lifetime. Is the system going to be unbound, remain bound? Is it going to merge, or is it going to continue as two separate stars, or a separate star and a remnant? Will there be a remnant at all? During the population synthesis stage, we need to consider this, identifying effects such as accretion, compact object mergers, and gamma ray bursts as well. That means we also need initial inputs of period and mass ratio, and we're going to need additional atmospheres, because the stellar populations that result from binary interactions are shifted in the Hertzsprung-Russell diagram. They're going to end up in regions of temperature, gravity, or composition parameter space that are not accommodated by traditional stellar spectral libraries. But the result is that we end up with an awful lot more potential outcomes. For a start, we can now predict anything that is fundamentally binary in nature, such as X-ray binary number counts or gravitational wave chirp rates. Through modelling these stellar interactions and their impact on evolution, we're going to change the supernova distribution. And we're going to change the gamma ray burst distribution as well. If we have interior structure for each star, so detailed models, we can start looking at things like spectra, and we can start to look at the impact of these very massive stars and their properties on the stellar absorption and emission lines, particularly for wind lines in the ultraviolet spectra of these galaxies. So binary population synthesis, it's been around for a while. There was a lot of very detailed early work in Brussels, for example, but perhaps the most dominant model framework that is now currently used was developed by Jared Hurley et al. In the early 2000s and is known as BSE, Binary Stellar Evolution. This uses simple analytic formulae to estimate the evolution of individual stars based on calibrations derived from a small calibration grid calculated in the late 1990s. More recently, we've seen a few more detailed stellar evolution models. So Poseidon, for example, is an important project that uses maser modelling to look in detail at the structure and interaction of stellar binaries. So is able to capture the interior structure and the impact that has in a way that, for example, the BSE code can't. 7 is also built on detailed models, but is, I believe, an interpolator. It is trained on those models, but does not calculate new stellar evolution models in detail. But these kind of rapid population synthesis codes, or codes that are just looking at the outputs of the stellar models, are fantastic for stellar populations, rates, and the like. The advantage of that is we can some physics and analytic prescription and see what impact it has. The downside is that you then are losing the information about the composition, about mixing, about convective structure, and about potentially the remnant sizes, for all of which you need detailed models for. Binary spectral population synthesis codes are much rarer. In fact, I hesitate to say this because it's increasingly hard to keep track of the overwhelming literature that rains down on us. But to the best of my knowledge, the only one that's reasonably widely used is the code that Jan Eldridge and I developed using Jan's expertise on stellar modelling initially, and my expertise on galaxies and observation. We've now been working together for so long that we're interchangeable. This is BPAS, the Binary Population and Spectral Synthesis framework, and we use a huge grid of detailed individual stellar evolution models spanning 13 metallicities to explore the behaviour of resolved and unresolved stellar populations. We release a lot of data products on our website. We have a lot more which we don't release just purely on space grounds, but are always happy to discuss if people contact us. I said we have a lot of models. The last big data release, which was version 2.2, used 250,000 stellar evolution models. So this is moving on a fair bit from generation currently working on, which will have 7.5 million individual stellar evolution models. So, given this, is binary stellar population spectral synthesis a solved problem? Well, if it were, I wouldn't have a job, I wouldn't be here talking about it, and you wouldn't be interested. So I'm glad to say that the answer is no. There are still a lot of things that we do not understand. Perhaps one of the key ones, and one which may not surprise this audience, but always surprises the galaxy audience, is just how poorly we understand massive star evolution. So on this diagram, which is one that Jan generated for our annual review, we're comparing the Geneva group's non-rotating models to BPAS single stars. These are both single stars. These both have fixed mass. They should, by default, evolve in similar ways. And you can see that to some extent they do. But details of mass loss rates, of when those mass loss rates apply, under which conditions, the treatment of chemical composition, and treatments of things such as mixing and wind stripping, result in substantial differences, particularly in the post-main sequence and in the regime of Wolf-Rayet strip stars. Okay, so we can't even agree on how single stars evolve in the massive star regime. We can add to the fun, of course, because the Geneva group is best known for their rotating star models. Rotation introduces additional mixing. This is going to add fuel into the core, potentially extend the lifetimes, potentially make the stars burn hotter. So we see a shift in the HR diagram, and we see an additional number of stars which are rotating, making it over into this stripped atmosphere regime, where they have lost the outer blanket of hydrogen. But if you introduce binaries, you end up with a still more different picture, because now you have binary interactions which are resulting in stripping, which are resulting in material being dumped onto different stars, and so rejuvenation, stars having additional fuel mixed into them and potentially extending their lifetimes. Indeed, rotational mixing taken at its extreme can lead to what we call chemically homogeneous evolution, or in our case, quasi-chemically homogeneous evolution, because we don't claim to be doing it perfectly. All of which means that we are now generating many more strip stars, and in particular strip stars at lower masses than you would predict purely from single star models. Now in recent years, a lot of work by IAU and others have actually gone out and looked in the ultraviolet. You can see that these are very, very hot stars, and identified a number of strip stars in the local group of galaxies. So these have been observationally confirmed. More importantly, though, ever since the mid-2010s, we've been pointing out that you need these to explain the spectrum we see in distant galaxies. Okay, we can't observe individual helium stars in those galaxies, but there was no other way to explain helium stars, to explain the ionizing spectrum of distant galaxies, if you don't have a method for effectively making strip stars at a range of masses. Now, as I said, much of the difference between the single star models and to some extent some of the other differences we're seeing here boil down to uncertainties in how we treat individual aspects of stellar physics. A very big one, particularly at the very massive star end, by which I mean stars greater in mass than 100 solar masses at birth, is the impact of mass loss rates. Okay, many of the population synthesis models are still using the mass loss rates of Vink et al. 2001, which work extremely well in some regimes. But it seems fairly clear now that very massive stars may be following different wind prescriptions. So here I'm just showing a comparison between the Vink 2001 mass loss rates and the mass loss rates by Grafner et al. For stripped but still hydrogen burning very massive stars. And you can see that this fundamentally changes the evolution. At high metallicities, it shifts you in the HR diagrams. At low metallicities, you go off in a completely different direction. These stars are massive enough and strong enough that you may well stick them sensibly well before the end of life. But how effectively does depend on your mass loss rate prescription. And although we are getting increasing studies of this, both computationally and observationally, it remains challenging to identify large observable populations of massive and very massive stars in these kind of regimes where these mass loss rates can be calibrated observationally. Of course, binaries complicate everything. In the previous plots, I was just showing one stellar evolution track at each mass. By comparison, this is showing a subset of possible binary models on each track. We typically calculate around 250 binary models at each mass, which is partly why we need these huge grids for populations. Of course, not all of these models are equally likely, but nonetheless, we show that there's a very wide range of possible outcomes to any given initial primary mass, depending on what its binary companion is and what that binary companion does to its evolution. I think I've already said that, yes. So we need inputs of binary parameter distributions. I've already mentioned this study by Mo and Di Stefano, which has the fantastic name of Mind Your P's and Q's. For the non-Anglophones out there, this is a saying, and Q's represent thank yous. So this is saying be polite. But in this case, it's the interrelationship between period and mass ratio. And you can see that Mo and Di Stefano parameterize these into a huge table. I don't expect you to read this table. It gives the frequency as a function of mass, but also period and mass ratio in a range of ranges, and also looks at the possibility of twins. And this is great. It is highly empirical, and there are large uncertainties on a number of these parameters. Okay. It was also only measured in the range of 0.8 to 50 solar masses and for resolved stellar populations in the local universe, which means primarily population 1 metal-rich stars. So we can ask the question, do these parameter distributions apply in other regimes at lower metallicities? Are these parameterizations universal? Again, it's very challenging to actually find observational data to constrain this, particularly at low metallicities. A few years ago, I had a go at sampling from the Mo and Di Stefano parameters, which are indicated by the blue points here, to generate a large number of possible SpecSynth models, each of which got slightly slightly different ratio distributions, just to look at what regime of uncertainty is left by the Moe and DiStefano models. And the outcome for that was at near solar metallicities, the uncertainties are relatively small. So things like the ionizing photon production, that's what powers H2 regions, has a relatively small range. The impact on the HR diagram is, or in this case, color diagram, is relatively small. The impact on the spectrum just puts a little bit of scatter on the spectrum. It will because you don't know exactly which binary parameter distribution you should be using. At low metallicities.
Sorry, Elizabeth.
Sorry?
We are having sometimes problems with the connection. I don't know if it's related to the problem you told me before. So
I haven't seen any problems at my end.
Okay, because maybe you can check if there is anything wrong.
Yeah.
If not, we can continue. But
don't see anything. I will stop sharing and I will reshare. I'll reshare
okay,
on this
just in
screen
case.
rather than a different screen. If anybody has any questions that they want to type in the chat, now would be a good opportunity to do so.
The point is that your talk is so nice that it's a pity that we miss from time to time part of what you're
Yes, no, I
telling.
understand. Can you
Okay,
now
let's
see
let's
that
try,
screen?
and if something happen, I will tell you. So let's continue and we'll see.
Okay. So, as I was saying, yes, we don't know what the binary parameters are, but we can estimate that there's some uncertainty. Now, since I did that work, which is 5 years old now, there have been additional early constraints on low metallicity binary fractions. Inevitably, these are based on small populations and on precisely 2 galaxies, which does lead you to question whether they are universal. But nonetheless, they're providing a reasonable indication that the massive star binary fraction remains high at low metallicity. And they're starting to provide constraints on the mass ratio distribution as parameterized by this period index. This is recent work by Hugh Sana. There's been additional work by Maxwell Moe's group in the LMC. So this is that power law slope for the initial period ratio. And they find a best fit of minus 0.34. For the SMC, that would put you over here, which is slightly concerning because it suggests that different studies in our local universe are showing a period index that goes down to from the Milky Way to the LMC and back up again to the SMC. With 3 data points and 2 trends, I think it's clear that we need more data in order to pin this down with any degree of accuracy. But nonetheless, it is suggesting that the binary fraction remains high, that many of those binaries are going to be in close periods, and therefore that modelling a range of possible binary populations in close periods remains a scientifically interesting thing to do. But that's not the only question for binary parameters. We can go back even to the single star parameters, and we can start asking questions again about the initial mass functions. Because we traditionally use the Salpeter law. Until very recently, galaxy people were using the Salpeter law all the way down and all the way up in mass. But we're now fairly sure about a few things. We're sure that the Salpeter law does not extend infinitely low. We now know that it's probably not universal. So is there a true slope? And if so, what is it? And we know that we have to ask questions about very massive stars. Do they follow the same slope? Do they follow a different one? And where do we put our upper mass cutoff? We can ask another question, which is, should the IMF be sampled stochastically? In other words, if you have a single 300 solar mass star in your population at early times, at young ages, you may outshine a substantial fraction of the rest of the population. But are you going to have one 300 solar mass star? No. On average, you're probably going to get something like 0.1 300 solar mass stars. But does it make sense to put 0.1 of a 300 solar mass star into your integrated spectrum? Probably not. But then we get into probabilities, of course. How do we sample? What is the distribution at this top end? And what impact will this have on the ionizing fluxes? Again, this is something I've explored, looking at a range of cluster masses for the initial stellar population and sampling stochastically from the IMF until I run out of mass. So these models will either have one very massive star or none. Well, the very high mass ones might have a couple of very massive stars, but they will have an integer number of stars in each mass range. And you can see that as soon as you start going below about 10 to the 5 solar masses in your clusters, you're starting to see the uncertainty here parameterized in the ionizing photon production expands enormously. Even at the high mass clusters, you still get scatters of several tenths of a dex, and that is significantly more than the error bars that observers are now claiming to be able to measure on things like N-ion from distant galaxies. Okay, so how you interpret those ionizing fluxes, either in local H2 regions or in distant galaxies where you're seeing the integrated light of many H2 regions, is quite strongly sensitive to your assumptions when it comes to sampling. The same, of course, will be true of your number of supernovae. The same stars which are generating ionizing flux are also generating supernovae. And whether or not you have at least one supernova in your population is a strongly sensitive to the mass of the cluster you start with. But it's worth noting that even very low mass clusters, on rare occasions, will generate massive stars that can go supernova. But the result, as I said, is that you do have quite large uncertainties on interpreting ionizing flux and supernova rates, particularly from dwarf galaxies, from individual star clusters, and from galaxies with very low star formation rates. If you're in a system with a very high global star formation rate, or where you're averaging many clusters, most of this probably averages out. But we're now in a regime where we try and do these studies in detail in individual places. Okay, I've already mentioned that there's a turnover at the low mass end, and I wanted to point out this very interesting recent work from Hennebel and Grudich, which shows that even for very massive stars, well, even for moderate mass stars, the uncertainty on what the true IMF slope, gamma IMF, is spans an order of magnitude, okay, between different studies observed in different environments. Now, this may be well known to the massive stars community, but if so, it needs to be more widely advertised to the high redshift community, because there's an increasing focus on looking at very distant galaxies. And many of these studies of very distant galaxies, in this case a galaxy at redshift 11, have tried to infer the IMF slope for massive stars based on SED fitting or analysis of the nebular emission and the ionizing spectrum. Okay, so there was, of course, the work by Schneider in 30 Doradus, which is a very nearby resolved stellar population. But a lot of these studies of the more distant galaxy population are now predicting IMFs in this kind of regime, with slopes which are more than one away from the salpeter slope for very massive stars. I do repeatedly remind people that these massive stars need to be put into context. So if you're starting with a salpeter slope of minus 2.35, sorry, this is an alpha, which is the solid black line here, and you're claiming from your analysis of the nebula spectrum that the IMF for very massive stars is -1, then your implication is that 99% of all of your stars are at masses greater than roughly 10 solar masses. Now, perhaps, but nobody has yet shown a convincing reason why that would occur. And it's very easy for people working on unresolved stellar populations to treat something like the IMF slope as a tunable knob and just adjust it until they have something that fits their data. It's always worth reminding people and talking to your colleagues in your own departments about the fact that massive stars do have physics behind them. And if you're going to claim you're not generating any stars less than 10 solar masses, you need to explain that. You need to come up with a physics motivation for it. Another thing that is strongly exercising the extragalactic community, and of course has implications for the local universe and for massive stars in our dwarf satellites, is the changes in composition that occur as you shift to lower metallicities. So those of us working on massive stars in the local universe are used to considering populations very close to solar metallicity, which would be 0, 0 on this scale. Okay, but as you move to lower metallicities, you are looking at stellar populations which formed at earlier times. Because they formed earlier, they formed in an environment which was not enriched by processes with long timescales, such as type 1a supernovae. Type 1a supernovae have generated most of the iron in the local universe, and the result is that if you look at lower metallicity populations, you also see a depletion of iron relative to oxygen and other elements which come from massive stars, more generally alpha elements, so alpha process elements. So for local resolved stellar populations, we're still, even with the SMC, we're still down at this end of the plot, at the near solar end. In the distant universe, we are now firmly up in this regime, the low metallicity regime, where we need to start thinking about alpha enhancement. And this is critical because until very, very recently, there simply have not been any massive star models run at alpha enhanced compositions. There's been an implicit assumption that if you've matched your iron, you're going to get the right answer. We've made that assumption ourselves, but it's one which we're increasingly questioning. So my colleague Connor Byrne, who is now an independent postdoctoral fellow, published a paper last year where he actually ran a detailed, extensive grid of massive star models, well, models across the full mass range, with different compositions, to look at the impact of changing the alpha element composition on opacities, on nuclear reaction rates, and thus on stellar evolution tracks. Perhaps the most obvious thing in this particular plot is that low mass stars at this end have shorter lives if they are alpha enhanced. But most stars, and in particular the massive stars, are hotter and bluer if they have a higher oxygen abundance. This isn't too much of a surprise because, of course, if they have a higher oxygen, they've got weaker iron at fixed Z. However, there are subtleties in this. Massive stars at high Z also have smaller radii if they are alpha enhanced. Okay, this is going to have an impact on the frequency of binary interactions. It's also going to have knock-on effects for things like mass loss rates and thus on the end state of stars. We're currently running our full binary grids now. These are single star models that were published last year, but in the process of running our binary models, we have also, I say we, Connor has also gone back and put quite a lot of effort into recalibrating the population synthesis, the rapid population synthesis equations of Hurley et al. We've put that back in the BSE code to have a look, and we find that about 10% of stellar end states are changed. So stars are moving from being black holes to neutron stars to white dwarfs, and vice versa. And within each of those bins on the diagonal, which are 1 to 1, there are, of course, changes in the mass of a remnant as well. This work should be submitted within the next week or so, and we would strongly urge people to use recalibrations, particularly for the massive star end. The original Hurley equations were never calibrated beyond 50 solar masses and had very few models beyond 30 solar masses. Our models are calibrated out to the full 300. The other thing we've been working on in terms of composition is looking at the impact of stellar spectral libraries, because an embarrassing fact, as well as predicting different evolution, different codes also predict different spectra for different stars. If you look at an empirical library versus a theoretical library, or between models covering different wavelength ranges, you get really quite different behaviour, particularly at the cool star end, but also for stars of moderate temperatures. So I've been running a series of CMF-Gen, massive star atmosphere models, which are challenging because, of course, we're looking at hot massive stars here. We're looking at large diffuse atmospheres with strong winds, which means we have to consider non-LTE. And as I said, I'm using John Hillier's CMF-Gen code to do so. So this is very much work in progress. I'm starting to write it up now, but I've generated large grids of stellar atmosphere models in which the only thing that differs between models is their composition. So here I'm showing a comparison between 2 models at fixed iron, 2 models at fixed oxygen, and 2 models at fixed total metallicity. And you can see that your spectra look similar. I mean, undeniably they look similar, but the details of the wind lines, the details of the continuum normalization, and this is crucial for H2 regions and distant galaxies, the details of the ionizing flux in the ultraviolet, well, the non-ionizing ultraviolet and the ionizing ultraviolet can be quite different between these models. So this is work in progress, but hopefully it's coming together, and I'm aiming to get this out this summer. But it does suggest that we need to be cautious when we're comparing to observations. Increasingly, observations are reaching the level of detail and precision where differences like this can be significant and will affect the interpretation between different spectra. Finally, I'm just going to wrap up with what might be a slight aside, but is also intended as a caution, which is to note that there is ambiguity that has become apparent in what we mean by the term stellar mass. Okay, those of you working on individual massive stars, on resolved stellar populations, you're able to count your stars and estimate the mass of each, and that's great. But people who are quoting the stellar mass of a population, of a galaxy, of a cluster, or using those galaxy and cluster masses to estimate things like supernova rates or gravitational wave transient rates, are using different definitions of what is meant by mass. At least this appears to be true to me. The key problem is that SPS models, all the way back to Beatrice Tinsley, have typically assumed that all of the stars in our population have reached the zero age main sequence at the same time. And that is simply not true. For stars which are low in mass, they can have extended pre-main sequence lifetimes before the onset of nuclear burning. Now, these can range from 30 mega years up to even a giga-year for low mass stars. And for the young stellar populations, which are now the major subject of our study, they are in this kind of age range. This means that stars below a certain mass threshold are not contributing to the light, or certainly not the optical and ultraviolet light of stellar populations. That means that if you're using a mass to light ratio conversion or an SED fitting algorithm which includes a mass to light conversion, which many of them do, you are not accounting for the stars which are yet to be born. Now, this is not a huge effect, but in the optical, about 10% of the light in the optical, 5,000 angstroms, is coming from low mass stars. Okay, and that means that you are going to be misestimating the age of the stellar population if you do not account, not the age, the mass of the stellar population, if you do not account for this. Because we're currently in the embarrassing situation where SED modelling typically accounts for the stellar death, so does not count stars which have died and become compact remnants, but are including stars which are yet to be born, and thus are giving a mixture of nuclear burning and yet to be born stars, but not post life stars. So the main thing is that this is a definition which needs to be treated with care. It is going to have an impact on young stellar populations, and thus on any stellar population that is studied in the UV or in the distant universe in particular. But the bottom line, because I realise I've run on a little, is that for those looking at young low mass star forming or low metallicity galaxies or stellar clusters or even populations of massive stars, observations and the simple stellar populations derived from them are pushing the limits of our understanding of massive stars. Those limits are constantly being pushed back. There is a lot of work being done in every area I have mentioned. But the cumulative systematic uncertainties that arise from things like the population parameters, the atmosphere parameters, and the stellar evolution can offset results based on assumptions from different modelling codes. Okay, so it's always important to take note of which SSP model, which stellar population and spectral population synthesis is being used, and its input physics. So having rambled on a little longer than I intended, I will stop there and I will ask if there are any questions.
Thank you very much, Elizabeth. This has been a fantastic talk. The problem was solved when you do whatever you did. So it's great to have the second half without any problem.
I'm
I
sorry for the
really love
problem.
it. No problem. I really love it, and I'm sure there's going to be a lot of questions. If not, I have some question myself, but I will leave first the opportunity to the audience. Any question here? not for the moment, so I will start. So it's not exactly a question, but it's a thought that so when you are talking about the IMF, and then you are mentioning something that now everybody has finally realized about the impact of binary evolution. What are your thoughts about how we compute the IMF?
Mhm.
Because nowadays, even if we are studying stars in the main sequence, this is not necessarily providing us any IMF. So what are the
Yeah.
thoughts?
So I had a look at this when I was playing with varying VIMF. Sorry, I've just stopped sharing my screen so I can see everyone. Um, uh, the way we handle it in BPAS, and I think the way most population synthesis handles it, I think it's how Pavel Krupa recommends it, I believe, is that we select our single stars and our primary stars from the IMF, and then we assign the secondary stars according to the binary parameter distributions. Okay. Now, what that means is that the secondary stars are not technically drawn from an identical IMF to the primary stars, but their frequency depends on what the primary star weighting from the IMF was. Now, that is one way of handling it. I had a look. It can change the slope of the true IMF from the inferred IMF by 0.01, 0.02. I would say that's in the noise, given our uncertainties about what the true IMF is. It very much depends what kind of mass range of stars people are most interested in. For the very massive stars, you can more or less assume that they're all in binaries. And in that case, the uncertainty is not really so much in the IMF as in the binary parameters. If does your 100 solar mass star have a 50 solar mass companion or a 90 solar mass companion? Or does it have a 10 solar mass companion? Because that will give you a very different apparent behavior to your population. But yeah, it is a challenge. How do you define an IMF in a binary stellar population when the primary and secondary are doing different things on different timescales? It's quite hard to determine.
Mhm. But even from an observational point of view,
Mm.
when we saw apparently single stars, and we compute all these plots you put about IMFs, observational results, these were obtained from measurement of masses that not necessarily are stars born as single. So then
Yeah.
all the conclusions there are, yeah.
It's very challenging. Most studies looking at the IMFs, I'm sure you know, make an attempt to comment on what impact a binary fraction and evolution since zero age has had on the stellar population. I don't know that there's a good way of doing that except by running many population synthesis models and using them to infer the range of possible IMFs that would lead to the observed
Mhm.
population, which would be how I'd have to recommend doing it. I don't think it's as I said, because the distribution in companions is typically fairly flattish. Um, it doesn't have a huge impact on the observed IMF uh, at most stages, but I'm not aware of a study having been done which has really explored that in detail. I might have missed one.
Mhm. Okay, thank you. Any question by the audience? We have a very good opportunity to ask Elizabeth directly. Everything was clear from from your talk.
I'm sorry if I rambled.
Yes, please, Surtita, if you want to.
Hi. Uh, Very nice talk. I was just wondering if you didn't mention much about the limitations of the stellar models that goes into BPAS.
Yep.
And I was wondering how sensitive your predictions are to the uncertainties in those.
I mean, I think that's a completely fair question. I didn't give too much detail about BPAS, you're right. BPAS itself is built on a grid of models which were constructed with what we consider to be a variant of the Cambridge stars code. So this is a code that in its primitive form was developed by Peter Eggleton in the 1970s and 80s at Cambridge. It was what Jared Hurley and Christopher Tout and their teams used to calibrate a lot of the analytic work on stellar evolution. It's a 1D stellar evolution model which treats the star as shells and calculates the transport of energy and indeed matter between shells, and iterates to find a solution at each age step, taking into account the stellar evolution. For binary interactions, we track two stars. BPAS in its current form has traditionally used an approximation for the secondary and then gone back and recalculated the secondary in detail, because running two stellar models in parallel, as anybody who's tried it with Maser knows, is incredibly slow. Okay, you're wasting a lot of cycles on a star that's going through a main sequence evolution, when you really need to be focusing on one that's going off the main sequence, or is being stripped, or is doing something more interesting. So the two options are to evolve the two stars in parallel, wasting computer cycles, or evolve one in detail while tracking what the secondary is doing to it through approximations, and then evolve the second in detail, taking into account any mass transfer or interaction. And that's the approach we've taken. We are exploring a full side-by-side binary code, but it runs orders of magnitude slower than the method we currently use. And so a model that would take half an hour with our current code would take weeks, days to weeks, with a full side-by-side binary code. But you are right that there are limitations. We run with a certain number of grid points. We run with certain assumptions. We run with certain assumptions about mixing lengths and interactions, certain assumptions about dredge up and what's going on, and we do have to pause and approximate occasional things. So we have to have a prescription that gets our models through common envelope evolution, for example, and we have to take that into account. I think the point I wanted to make, though, was that every stellar evolution code has its own set of flaws and uncertainties. It has its own set of assumed physics, its own parameterization for different stellar evolution stages or for different mixing. Maybe hydro simulations could arguably be doing it better, but you're making approximations there, and you're running so much slower that you can maybe make one star a year rather than tens of thousands. So you always have to, I'm not saying that any of these codes are free of assumptions. I am saying that understanding what assumptions are implicit in your analysis is the important step. Is that clear? I don't know if I answered your question.
Yeah, I was like more interested to know about the microphysics. For example, I have discussed this with Jan a bit about the implementation of differential rotation, which is
Okay.
very important for angular momentum transport in a
Yep.
system. So yeah, about that.
Yes, I would say that rotation is an area we know we are particularly weak in. We work in mass coordinates rather than angular momentum or gravity coordinates, and that makes the distortion due to rotation very difficult. We do actually have programs underway, and in fact one of the things I think I'm going to get my incoming PhD student to look at is whether we can approximate the impact of rotation better using different mixing assumptions, because fundamentally the main impact of rotation is on mixing. But you're right, also angular momentum transfer and how that's handled. So I think for detailed microphysics is something I'm going to have to direct you to our papers or talking to me or Jan about offline. But I hope that answered the broad thrust of your question.
Yes, yes. Thank you very much.
Any other question? Okay, if not, I'm going to read this that Andrea Sander wrote. Thank you, Elizabeth. You gave a great overview, bringing the often very different perspective. I think this is a very valid comment because sometimes it's not so easy to connect the different communities. And now, as usual, if you are watching this in the future and you're interested and you have questions for Elizabeth, I'm sure she will be really happy to answer you back either by mail or contacting her directly. So thank you very much, Elizabeth, once more. Has been lovely, this talk and the possibility to meet you again.
Thank you very much. And yeah, by all means, get in touch. If I don't answer straight away, feel free to send me a bugging email a week later. Okay?
Okay,
Thank you.
perfect.
Bye.
Thank you very much and see you soon.